What is a Markov decision process, MDP, in reinforcement learning? Imagine you're trying to teach a robot how to navigate a maze or play a game. How does it decide what to do next? That's where a Markov decision process comes in. It's a way to model decision-making in situations that involve some randomness and some control. Think of it as a set of rules that help the robot figure out the best moves over time. A Markov decision process has 5 main parts. First is the state space. This is all the possible situations the robot can be in. For example, in a game, a state could be the current position of the robot or the game score. Next is the action space, which includes all the moves the robot can make from each state. Moving left, right, or picking up an object are examples of actions. Then there's the transition probability. This tells us how likely it is to go from one state to another after taking a certain action. It captures the uncertainty in the environment. For example, if the robot tries to move forward, there might be a chance it slips or hits an obstacle. The reward function assigns a numerical value to each move, showing how good or bad that move is. For example, reaching the goal might give a high reward, while hitting a wall gives a negative reward. The last component is the discount factor, which is a number between 0 and 1. It shows how much the robot cares about future rewards. A low value means it prefers immediate rewards, while a high value encourages planning for the long run. The Markov part means that the next state depends only on the current state and action, not on how the robot got there. This simplifies calculations and makes modeling easier. In reinforcement learning, the agent interacts with the environment modeled as an MDP. It observes the current state, chooses an action based on a strategy called a policy, gets a reward, and moves to a new state. The goal is to find the best policy that maximizes the total rewards over time. This approach is used in many real-world applications like robots learning to walk, self-driving cars making decisions, or game-playing programs. Understanding Markov decision processes helps us build smarter AI systems that can learn and adapt in complex environments.